Dear students, today's video lecture will deal with the registers. As you all know, registers are the storage devices, but with a few exceptions. First of all, they are small capacity storage devices, means their capacity is in terms of bits, either 4-bit or 8-bit or 32-bit, etc. And they are short-term storage devices, means they store temporarily for intermediate or auxiliary storage. So registers are the small capacity and short-term storage devices, and of course they are formed by using flip-flops. We will see it a bit later. First of all, they have two different categories: buffer registers and shift registers. So let's take them up one by one. First of all, buffer registers are made up of flip-flops. Depending on the storage capacity, number of flip-flops can be had accordingly. So in buffer registers, there's no connection between the flip-flops at all. This flip-flop D flip-flop stores 0 and 1. So this D flip-flop has no connection with this and this. Of course, they are fed by a common clock pulse for synchronization, but they do not share data with each other. This flip-flop, first flip-flop stores data independently and it gives output independently. Similarly, this flip-flop also, second flip-flop also stores data independently and gives output independently, and similarly the third flip-flop. So they have no connection, means information is stored in individual flip-flops. But this will be very clear when we study shift registers. In the shift registers, data shifts from left flip-flop to the right one. Then it becomes right shift register, or data may also shift from right flip-flop to the left one. In this mode, data will be shifting from right to left, so it will be known as left shift register. So before going into their circuit diagrams, let's categorize them. They are basically of four types. First type is serial in and serial out. Basically, this categorization is done on the basis of the style of input and output. So input is done serially and output is also done serially. So input will take place from one side and that data will shift from left to right and so on, and at the right end output will be eked out. So serial in, serial out shift registers. Secondly, we can have serial in, parallel out. So in such flip-flops, input will take place serially and output will take place parallelly. So one port for input and data will be shifted, and when we are to take the output will be taken from the individual flip-flops simultaneously. So feeding data into the registers is known as loading. Feeding data to the shift register is known as shifting, and taking output from the registers is known as loading. So shift and load are the processes of input and output basically. Thirdly, we can have parallel in, serial out. In such kind of flip-flops, input will take place in a parallel style, means all the flip-flops will be fed input individually at the same clock pulse simultaneously, but the output will be received by shifting of data. This data will be output first and this will be shifted and so on. So third category is parallel in, serial out, and obviously last category parallel in, parallel out. So both input and output are done in the parallel style. So let's take them up one by one and also have their circuit diagrams. First of all, we have serial in and serial out. This circuit is a 3-bit register because it is using 3 flip-flops, FFA, FFB and FFC. And we are using data flip-flops. Data flip-flop using is very simple. If you want to store 0, feed 0, and if you want to store 1, you feed 1, right? And of course all of the flip-flops are negatively edge triggered and they are fed by a common clock pulse. So they are synchronous, means all the flip-flops will work in tandem. Now the circuit is designed in such a way that output of first flip-flop is fed to the input port of the second flip-flop, and similarly output of the second flip-flop is fed to the input port of the third flip-flop, and this is the output port. You can have Q outputs, you can have QA output, Q complemented outputs also. This is just a provision, but we will focus on this only. So data will be fed at this port. So working can be understood in using the pulse diagram. So this is the clock pulse, and we are having negatively edge triggered flip-flops, so they will be active when there is a negative edge in this clock pulse. So first of all, let us suppose data 1 high signal is input at this port. This high signal will wait for the negative edge. So whenever there is a negative edge, first flip-flop QA will store a 1. So this 1 will now be available to the second flip-flop at the second clock pulse, second negative edge of the second clock pulse. So QB, on reaching the next clock cycle, next negative edge, this flip-flop B flip-flop will receive input from A flip-flop. So this will also become 1. So that means this data will be shifted to this port on the next negative edge. So every negative edge, at the every negative edge, data from this flip-flop will shift into this, and data from this flip-flop will shift into this. So earlier we had zeros. In the beginning all the flip-flops are reset to 0. Suppose 1 is fed here. So at the next negative edge, this 1 will be stored in this flip-flop. But earlier it was storing 0. That data will be stored in this flip-flop, and this data from this flip-flop will be stored in this flip-flop. So at the negative edge, first negative edge, when you feed 1 signal here, this flip-flop becomes 1. So now input for the second flip-flop, B flip-flop, is now 1. So at the next negative edge, this flip-flop contains 0, this will be fed to this flip-flop. This flip-flop contains 1 and it will be fed to this flip-flop. This flip-flop becomes 0 again because there is no input. So at the first negative edge, this flip-flop becomes 1, this is 0 and this is 0. Similarly, at the next negative edge, this one will be shifted to this flip-flop and these two flip-flops will be 0 now. So data shifts from left to right flip-flop. So you get a flip-flop which shifts data from first flip-flop to second, second to third. So time taken to complete input in this flip-flop will be 3 clock cycles. So this flip-flop, this data will be maintained in the first clock cycle, and the second clock cycle, in the second clock cycle this will be fed to the second flip-flop, and at the third negative edge it will be fed to the third. So the time taken by this register to complete input is number of registers, and depends on the number of flip-flops. If it is a 3-bit shift register, it contains 3 flip-flops, and these 3 flip-flops will be settled in 3 clock cycles. So for input 3 clock cycles will be taken, and if it is a 4-bit register, it will consume 4 clock cycles, and so on. So 3 clock cycles are taken for input, and similarly 3 clock cycles will be taken for the output also. So shift register is a comparatively slow device. Similarly, we move on to serial in and parallel output. So for this we are having, so this diagram deals with 4-bit shift register as it contains 4 D flip-flops. In this diagram we are having all the flip-flops positively edge triggered. So this time I have taken a different edge triggering so as to make you people clear that what happens when there is positive edge triggering and what happens when there is negative edge triggering. This time we have positively edge triggered flip-flop, and the common clock pulse is feeding all the flip-flops. So this is a synchronous device again, and this is the clear signal. This will be used to start the operation. So to clear all the previous data, this will be pressed to 1 and all the flip-flops will be set to 0. So now data, as you can see, the input is taken in the serial mode. So data will be fed from this port, single port. This data will be shifted to first flip-flop at the first negative edge, and at the next negative edge this data will be shifted to the second flip-flop, and this flip-flop will contain the new input. So 2 registers have now stored 2 bits of information. At the next negative edge, this data will be shifted to this flip-flop B, and this data will be shifted to this flip-flop C, and new data will be shifted to this flip-flop D. So now at the third negative edge we have 3 flip-flops ready with input, but it is not complete because we have to feed 4-bit information. So at the next negative edge, data from B flip-flop shifts to A. Similarly, data from C shifts to B, data from D shifts to C, and the last bit of data is stored in D. So this register takes 4 clock cycles to complete the input. Now when output is taken, you can see it very clearly. Output of every individual flip-flop is eked out at this port. So you can take output from these terminals simultaneously. So whenever there is a positive edge, these flip-flops will provide you output, but after minimum 4 clock cycles have been lapsed. So these 4 clock cycles will be used to store the data. So in the 5th clock cycle, output will be taken out. As you can see, 4 clock cycles will be consumed for input and 1 clock cycle will be consumed for output in this case. As in case of serial in and serial out output also took 4 clock cycle, but parallel output takes just 1 clock cycle. You can better see it from this pulse diagram. So 4 clock cycles are being consumed to complete the data. Data reaches at QD at the 4th clock cycle, and after that you can have output in just 1 clock cycle. Next we move on to the parallel in serial out shift register. This register appears to be a bit complicated, but it's not that much if you understand it very clearly. So first of all, you focus on this circuit, this portion of the circuit. This is having two AND gates, G1 and G2, and an OR gate. So all these AND gates are provided signal. So this signal, shift signal and load signal. Load is taken as complemented form. This means that if you provide 1, it will act as shift, means input. And if you provide 0, it will act as a loading, means output will be taken. So input or output process depends on this signal. So when you are to input, you put high signal at this port, and if you are to take output, you put low signal, 0 signal at this. So first of all, let's take input. So for input, we feed 1 here. So this 1 will travel to the AND gate G1, and this 1 signal after inversion becomes 0, and this 0 will travel to the AND gate G2. So G2 receives 0 and G1 receives high signal. So this will be blocked. Output of this gate will be 0, and output of this gate will be depending on the second input. So this AND gate will be carrying the output QD. So QD ended with 1, this will produce QD. So QD will be presented here, and this gate will be giving 0 output. So 0 and QD, or after ORing them, we get QD. So QD will be fed at this terminal. So if we provide high signal here, then this flip-flop receives this QD. So this if it is 1, if this terminal has the signal 1, this will be virtually a connection between QD to QC. So this this information will travel to this port. Similarly, the similar circuitry is provided here also. So if it is 1, this QC will be connected to DB virtually, and similarly QB will be connected to DA virtually. So so when this is 1, so this will be connected to this will be connected to this, and this will be connected to this. So it works as a serial data shift register. So as long as input is being provided, data will be shifting from this to this, this to this, this to this. So it will act as a serial in, right? And similarly, if it is 0, so 0 will be fed to G1, and this 0 after becoming 1 will be fed to this G2. So now this time G1 has 0, so it will block the output. 0, output of this gate will be 0, and output of this gate will depend on this. So this time when this is high 1, this output, this input will be fed to this terminal, right? And this will be traveling to this flip-flop. Similarly, this signal, instead of this, earlier this signal was traveling, but now this signal is traveling to this port. This signal is traveling to this port. So it becomes parallel. So when you are to feed input, you put 0 here. So while loading, while inputting signal, you put 0 here. So this data provided on terminals A, B and C and D will be provided to shift registers DA, FFA, FFB, FFC, FFD. But if this is 1, then data will be the connection will be like this. So it will act as a shift register. So while inputting, you put a 0 here, it will load data from in the parallel manner, and while outputting you put 1 here, so it will be connected in a serial manner, output will be provided. So input will be done in a parallel manner and output will be done in a serial manner, but you have to provide appropriate signal here. If you want to load data, input data, then you put a 0 signal here, and if you want to take output, means shift the data, you put a 1 here. Okay, let's now move on to the parallel in, parallel out. This is no different from a buffer register. All the flip-flops receive data in a parallel manner and provide output in a parallel manner. So a common clock pulse controls them to make them synchronized. So there's nothing complicated in this circuit.